today we start seeing how useful maximums and minimums are. A lot of the problems that you might run into as we get closer to the AP exam are not just, hey, find the max of this, or hey, find the min of this. They're going to tie it into a real-world type situation. So we're going to go right to an example here of making a box. And this is going to be a very simple box. It's probably going to be a very weak box, to be honest with you, because all we're going to do is take a square piece of cardboard, and let's say that the cardboard was 25, we'll just say inches this way, and it's 20 inches this way. And the way we're going to make this thing is we're going to cut out a corner on each one. Kind of like that. It's not a great drawing. But we're going to cut out a corner, and then we're going to fold up these flaps. That's why I said it's probably going to be a very weak and poorly made box. But we could still make a box that way if we wanted to. So then we're going to fold up those flaps, okay, and then tape the corners together or whatever, and it'll be a box. Well, one thing that you need to notice is that what we're cutting out squares. My picture's not great, but we are cutting out squares. So what we're cutting out, we'll just call that X. And all of those distances are the same. We're going to cut out the same square on every corner. So if I do that, what is this length in here? 25 minus 2x. Very good. And then the other length would be 20 minus 2x. This one running this direction. All right. Now, so here's our question. What do they want us to find? I'll write that over here. How large should x be, or my square, to get the maximum volume? We want a box that will hold as much sawdust as possible. Okay, if you think of something that has some volume to it, all right? It can hold as much sawdust as possible. So obviously, don't we need a volume formula? How do I find the volume of any old box? Length times width times height. And so this will be our function. All right? V of x will be my volume function, and we actually have all the pieces. I have the length of the box is going to be 25 minus 2x. Better put that in parentheses since it is a sum or difference, times the width, which is 20 minus 2x. And what is the height of the box going to be? Plain old x. Now what do? I've got a function. We're supposed to find the maximum volume. Don't I need to find the max? And haven't we learned ways to do that? Right? So we've got a little bit of algebra to do here. If I do FOIL with this function, I have 500 minus 50x minus 40x minus 4x squared, and that whole mess is still going to be times x. and I need a new page. So we're going to do distributive property through that thing. Yeah, that should be minus 40x. We're going to do distributive property through that thing and simplify it a little bit. My new volume function would be 4x cubed minus 90x squared plus 500x after I simplify and do distributive property. Now we're ready to start finding the maximum. You'll notice this 4 is positive. When I was multiplying here, this should have been a positive here because we have a negative times a negative. All right. So now we're ready to start our process of finding a max or a min, and this is a good review for us. The first thing I need to do is find v prime. The derivative of this thing would be 12x squared. Come on, marker. 12x squared minus 180x plus 500. Set that equal to 0. Why? To find what? Critical points. And aren't those the places where the slope of the tangent line is equal to 0? As a matter of fact, I think on your semester exam there's a question about a horizontal tangent line. Well, that's what these are. Okay, a horizontal tangent line is a place where there's a maximum or a minimum. So we set this puppy equal to 0. Okay, and this is a good place for the quadratic formula probably. And you're allowed to use a calculator. I suppose I could divide everything by 12, but I think I'd get a decimal over there for 500. So if you use the quadratic formula, I'm just going to put QF, quadratic formula, you get this. X equals 11.32, and you also get 3.68. I get two possibilities. This is where we need to use our noggin a little bit. One of those is a problem. Which one is a problem and why?
Probably.
Now remember what we're doing with this thing. Go back to our picture. Aren't we subtracting it? Like right here, I'm subtracting each of these from 25, and right here I'm subtracting each of these from 20. The 11 is a problem, because isn't one side of my cardboard 20? I can't subtract, we're going to double this thing. I can't subtract 22 from 20, right? This one is too freaking big. So it goes away. I can't use that one. I'm going to use 3.68. Okay? And now I need to determine what's going on at this 3.68. Should be a maximum, right? Now, haven't we learned two ways? We've learned first derivative test, second derivative test. I think it'd probably be easier to use second derivative test. Take the second derivative of this thing. The second derivative of my volume function would be 24x minus 180. And if you recall, using the second derivative test, I'm going to plug the critical point into the second derivative and see what my sign is. I'm going to do v double prime of 3.68, which will be 24 times 3.68 minus 180, and I can already tell that's going to be some kind of negative number. Negative what? Negative 91.68. So now I know that this thing is a max because I got a negative value when I plugged the critical point in to the second derivative. Now, all I have to do is, this is this 3.68, that is my x. That's my cutout. All right? What if I wanted to find that maximum volume? If I wanted to find the maximum volume that I would get on that box, I would need to plug in to the original to get the maximum volume. Okay, and I think that happens sometimes in homework or problems you see on the AP exam. Plug it into the original to get the maximum volume. So not into the derivative, not into the second derivative, we plug it into the original. So if I wanted to find V of 3.68, I'm going to tell you what that is, save us some time. It's 820.53 cubic inches, and that would be my maximum volume on that box. All right? Let's look at another example. Find two numbers whose sum is 20 and whose product is as large as possible. I'm sure these are the kind of things that you're thinking about when you're laying around the house on a Sunday afternoon. Maybe you just got done watching your favorite episode of SpongeBob or something, and you just said, I wonder what those two numbers are, that when I add them up, I get 20, and when I multiply them, I wonder, you know, the product is as large as possible. So let's figure out what these are. I've got two numbers. If I call the first number x, this is my first number. If that's the first number, what's the other number? Now let's use the same letter. Let's come up with an expression. 20 minus x. We don't like having multiple variables. That creates problems for us. The second number would have to be 20 minus x. This problem is actually not as difficult as the last one. Now, let's think here for a second. Don't we have kind of a little domain restriction on this thing? I mean, what's the biggest, can either of the numbers be bigger than 20? No. So I know that the x has to be in between 0 and 20. That's we would call that a domain restriction on our x. Now, whose product is as large as possible? That should be our guiding force, because isn't that telling us what we want the maximum of? We want the product of these two things, okay, of these two numbers. So the product, we'll just use plain old f of x, is going to be x times 20 minus x. That's what we want to use to find our extrema, is the product of those two numbers. Now, if it were I would go ahead and distribute that x and make it 20x minus x squared, because it will be so much easier to just go ahead and find the derivative of that puppy. So let's find the derivative of that puppy. I wonder what the derivative of a German Shepherd puppy is. It's my favorite dog. F prime of x equals 20 minus, there's my derivative. What do I do now? Set it equal to 0. So we're going to set 20 minus 2x equal to 0. Subtract 20, negative 2x equals negative 20. X equals 10. Does that fit in my domain?
Heck yeah, it does.
Heck yeah, that fits in my domain. So what should I do now? Well, we need to confirm that that is a maximum, right? Now, this is a case where the second derivative, look at what my second derivative is. Here's my first derivative.
-2, so it doesn't equal...
Wait. The second derivative is going to be -2, so it's always negative. So any number that I plug in, f double prime of 10, is also going to be negative because it's a constant function, so that is a maximum. Okay? So, the two numbers are, what are my two numbers? Whose sum is 20 and, isn't it 10 and 10? Right? 10 and 10. Okay, there's my two answers, 10 and 10. One more problem. This one's fun. Designing an oil can. Now, this is a little bit before your time, but just to keep people interested, even if you're taking notes at home from this, you know, back when I was a kid, oil came in a can that looked like this. And my area is not going to let me see it there. There it is. And that's the way oil came. Instead of in the plastic things that you see it in today, that's the way oil was bought and sold. So if we're going to design an oil can, we are going to have a right cylinder. Kind of like, in today's world, we could think of a can of Campbell's soup. Okay? A right circular cylinder. So let's say we are asked to design a 1-liter oil can using the least material possible. So we're trying to save money on our oil can. Save the environment, because we're worried about using too much metal. So, well, we need to come up with some formula work here. And first off, when I say a 1-liter oil can, isn't that referring to a volume? So we better start with the volume formula. Does anybody remember how to find the volume of a right circular cylinder? Area of the base times the height. And the base is a circle, and the height is h. So the volume of this right circular cylinder is pi r squared h. Okay? Now, there's something else that I know, and aren't I also talking about the material that I'm using? So aren't we also talking about surface area? Surface area is actually the one we're going to find the minimum of. Okay? So if you cut this this thing right here and unfold it, it's just a rectangle. Okay? The side of this can is just a rectangle when it's unfolded, and its length would be the circumference, right? So I'll just use, I'm going to use a different letter. I'm going to use H. No, not H. I'm going to use M for the surface area. I just need a different letter. So I'm going to have the circumference, okay, the circumference times the height. That will give me the area of the tall part. And then don't I have a top and a bottom? So I'm going to have to add 2 circles. Okay, a top circle and a bottom circle for the can. Well, the circumference, isn't that pi times diameter? Which is also pi times 2r. Yeah, we want to write it that way. So my surface area is 2 pi r h plus 2 pi r squared. Okay. Well, the problem here is that I have 2 variables. I have an r and an h. So I need to eliminate one of them. And that's actually where we're going to use this. Because don't I know the volume of the can? A liter. Now, the number 1 is kind of hard to work with. I mean, just to make sense of. Let's convert that. Isn't a liter also 1,000 milliliters? I think it will make more sense to us if we can see a concrete number here. The volume of this thing is going to be 1,000 milliliters equals pi r squared h. Okay. Now, what we can do now, if you look at my formula over here, I have an r in both places. I think it's going to be easiest if we eliminate this h. So let's solve this thing over here by h and divide both sides by pi r squared. And now I have that the height is equal to 1,000 divided by pi r squared. And now I am ready to plug that in to my surface area formula. And I will have that the height, the surface area is equal to 2 pi r times 1,000 over pi r squared plus 2 pi r squared. So we've got a little bit of simplifying to do before we can start tackling this problem. I've got an r situation. I can get out the slasher, and I'm going to be left with an r down there. Oh, the pi's go away here. That's good news. And so now my surface area function is 2,000 over r plus 2 pi r squared. And the good news is we've got a function with one variable. And we need to write this a little bit differently because we know when we take a derivative, it's much better to write this little deal here a little bit differently as 2,000 r to the negative 1. So let's write that as 2,000 r to the negative 1 plus my 2 pi r squared. And boy, there was a lot of work just to get ready to do this problem. The work to get ready to do the problem is much worse than doing the problem, I guarantee it. Because now all we have to do is find the derivative of it. Now we can just start finding, now aren't we looking for a minimum? We want to use the least material possible. So the derivative of this thing would be negative 2,000 r to the negative 2 plus 4 pi r. We're going to set that thing equal to 0 to find my critical points. At this point, I think it's going to be better to write it this way. Because now I can use an old pre-calculus trick, which is to multiply by the denominator to get rid of fractions. So if I multiply everything by r cubed, or r squared I mean, r squared times this, that's supposed to be an r squared, the marker went crazy. R squared times this, r squared times this, I still have 0 on the left, equals negative 2,000 plus 4 pi r cubed. Now, we do a little bit of algebra here. Take a 2,000 over, equals 4 pi r cubed. Divide both sides by 4 pi. Now I have 2,000 divided by 4 pi equals r cubed. And I can take the cube root, right? Yeah, this is a good place to have, you know, a calculator and find the decimal of this. We're going to take the cube root of both sides of this 2,000 over 4 pi and the cube root of r cubed. And when you do that, I think you get 5.42. Yeah. And 5.42 is what? Am I done? Do I have what I need?
That's your radius.
That's the radius of the can.
So you can go back to your
right?
function and find the...
And so what would I do to find the height?
Plug in your R.
Into what?
Your volume.
Into the volume. I would plug it into this expression that said that 1,000 equals pi r squared h. That's what I would do, is I would plug it into that one and find your h. Okay? Yeah, we already have this solved for h. We already had that h equals 1,000 divided by pi r squared, and then you can just plug it in there and find your height. Okay? So it would go right there. And we will stop there for today.